Hello and welcome back to Calculus 1. We are in chapter 3 talking about the derivative, and we already talked about the derivative as a function. Now we're going to talk more about derivative as a function. So last class we said that f prime of x was defined as the limit h goes to 0 of f of x plus h minus f of x divided by h, and it's a function, right? We also have seen that function f of x equals x squared minus 6 gave us f prime of x is equal to 2x, and we've seen, so that was example 1. Example 2, f of x equals 1 over x minus 2 gave us the derivative of negative 1 over x minus 2 squared. So we also said, and I'll write it again in blood, the derivative is a function which computes all possible slope of tangent line at a given point. All possible for a given function. For a given function f of x. So this is our this is what we covered last time. So function, so derivative is just a function, and we see that 2x, that's a function. You can draw the graph for it. This one is also a function. You can draw graph for it. So we know what happens there. So now let's take a look at the relationship between the function of the derivative and the original function. First, I'm going to draw the ones that we have up there. So example 1 and example 2. So example 1 was a quadratic function that went through negative 6 as something like this. So this is my f of x, the black, and now the red, 2x is my f prime of x. So quadratic function has the linear line as its derivative, and we see that over here, one thing that you can observe from this graph is that when you have a minimum value, the derivative goes to 0. Now that will be back many times, and it's the time now is the time to learn that important feature, because what happens at the minimum or a maximum value? You see that all of the incoming slopes on the original black line become flat, horizontal slope at min or a max. And we know that slope of the horizontal line is 0. Since derivative is the slope of the line, it makes sense to go through the origin, to go through x-axis, right? To have a 0 value at that point. So generally we just draw a little horizontal line at min and a max to signify that the slope is 0, and that's the place where the derivative has to cut through. There we go. The next example is the one that we have asymptote at -2, and we have our 1 over x graph, which is just shifted to the right. Now, if you take a look at the other one, the red one, so this is your f of x, the black. Now, the red one was -1 over x minus 2 squared. Well, this is the offshoot of 1 over x squared, and 1 over x squared looks like this. So if you think about this, it's very easy to draw the other one, because -2 is just shift to the right 2 units, and -1 is a reflection, so the derivative must be this. Very simple. Trying to make it symmetric. Whatever. So, from the first graph, we picked up that any time when you have min or a max, your derivative has to hit x-axis, 0, right? Y equals 0, which is x-axis. So it has to cross x-axis at that point. For the second one, we learned that the vertical asymptote location is preserved. So that's what we learned from the second one. So we are learning 2 things from the first and something from the second. Second one says vertical asymptote location is preserved as we go from f of x to f prime of x. So they have the same asymptote. In this case, x equals 2. On a previous picture, f prime of x goes through x-axis when f of x has min or a max. So those are the relationships that we are learning from the 2 examples we did last class, right? When we did the derivatives. Now we're taking a look at those and say, okay, what are the features between the 2 worlds, the world of a function and the world of the derivative? They're both functions, right? And they are related through that calculation that we do with the limit. Now, the derivative function measures the change of the f prime of x measures the change of original function, which is f of x. So now the question is, can you draw the derivative looking at the function without having the functions? Can you look at the graph of a function and draw the derivative? So say, let's come up with something. So here is, in black, here is the function f of x. So I just drew random stuff and it worked out to end in 19 nicely, whatever. The question is, what is the derivative graph? So I have my f of x graph. What is the derivative graph? Well, we look at it and we say, on this part over here, we have an increase. We have a positive change because we are gaining stuff. Do we see that? If this was a money graph, you would be gaining money over time. If it was the battery charging graph for the energy storage, it will be gaining energy, batteries charging. So whatever you want to think of in terms of application, from the graph we clearly see that we are gaining y over time. It's a positive change and it's happening at a constant slope of 2 because it's 2 over 1, right? So for this part I will draw a constant segment there because there is a steady increase. It's a positive increase, so it's at 2, right? It's a positive, it's a gain, right? It's a positive, it's increase. And it's happening in this interval from 0 to 2. And then, what happens now? No gain of any kind and no loss of any kind. So what's the derivative in this case? 0. Very good. The derivative now is 0 because there is no change. No change. Slope of the horizontal line is 0. There is no change in that. So we have to draw a piece on the x-axis. And then what happens next? Increase. So we are going to have another piece over here. Slope is 1 on that piece because we go 1 up, 1 over, 1 up, 1 over. And then what happens? 10 to 14? Another 0. Another 0 happens because there is no change. Again, no change. Piece. And that's that part. And now what happens for the last portion? It's a decrease, it's a drop, right? So that one will be a negative part like this because it is a curved drop, so it's not a constant drop, it's a curved drop, so we get to have a line like this. So that's it. You have your f prime now of x. All of this is in red. It's a piecewise function. It's okay to be piecewise function. So we have an increase, then stand still, then another increase, stand still, and then the drop as we go on following the function. I like this image in the book. It's maybe difficult to see all of the little tangent lines, but maybe you do see these red segments across. So observe that as the function is increasing, every single little line has a positive slope. And then at the top, which is the maximum, it has a slope of 0, it's flat. And then the slopes become negative as it starts losing the value. It's much faster to consider the derivative than to consider if you need to spot the change fast, like the stock market or something. You want to continuously look at the change and see if the money is going up or is going down. If it's going down, predictions are that, you know, maybe something will crash or something. Sell, sell, sell as soon as possible, right? Sometimes it's the gamble to make the investment hoping that they will bounce back. One of the examples now is this video game company, EA. It's falling apart with, right? But some predictions are that, you know, people should be buying now because they are going to fix things. Another one is the Blizzard Entertainment. So a lot of considerations in that. I can also think about driving, looking at the graph we just had. I am starting at the zero velocity, which is at the origin. I hope you start driving that way, right? You get into your car while it's still parked. So you are going to start driving from 0. And then you see increase in velocity, then flat velocity. Let's say you reached 55 miles per hour. Then you say, I won't get stopped, right? So you go extra, 10 miles per hour. There is the period that it takes to accelerate from 55 to 65. You don't get to just instantly change the... It doesn't matter. Even if you are driving Tesla, you still have to, spend a portion of a second to go from 55 to 65. It can't just be poof, it's there. So there is this time that elapses for you to change your speed from 55 miles per hour to 65 miles per hour, to accelerate right from one to the other. No, you see, woo, and then it's like, license and registration here at 19, right, because you stopped. It's a less grim example than a tire popping up at 65, because that might not be the best situation. Do what? So that will be it. And let's take a look. So they have same situation with a graph that looks a little bit different than mine. As you can see, the black and the red with negative slope, derivative is negative, positive slope, derivative is positive, that's increase, and then again a decrease and a negative slope. So you can see that the red line is below x-axis for all decreasing parts, and the red line is above x-axis for all increasing parts. So we are learning to put now everything in one spot. Number one, min-max on f of x give f prime of x equals 0. 2, vertical asymptotes stay, VAs stay as we go from f of x to f prime. So locations are the same. Number 3, increase means that the derivative is larger than 0. And 4, decrease means that the derivative is smaller than 0. So these are all of your rules in one spot. Maybe if I change, you can actually see what I wrote. Good thing you all mentioned immediately. It's Saturday, you should be happy. You love weekends, right? Anyone? I'm just gonna bring the bottle to class. I might as well start it. So these are all of the rules in one spot. Amazing example over here. Look at that. Draw the derivative. You say, easy. Max, min, max, 0, 0, 0. And then you just snake the rest of the function looking at the increase, decrease. See, this one is the increase part, so it has to be above, then dips below for decrease, then goes above for increase, and then dips below for decrease. It's an amazing example. To see the way you draw the function, the derivative function, looking at the original function. Okay, let's go to homework. Oh, here's another example where you preserve your asymptotes. So let's go to homework. There they are. Look at 51. Can you have a better example than 51, right? Let's draw a derivative for problem 51, and that ends the lecture. So I'm just going to draw this. The same you should draw as well. We have asymptote at -2. Another asymptote at 1. Okay, so I'm gonna make this wider then. At +1. Good. So what do I have? This. There we go. So where do we start? Well, we immediately find the max value, and that's where the derivative goes to 0. We know that these asymptotes stay where they are. So what do I have? I have a decreasing function on the over here. It's decrease. So if it's a decrease, the slope needs to be negative. I mean, yeah, the slopes are all negative. So that piece stays as is. Then we have the increasing function, which means your derivative has to be above y-axis, and it has to go into a 0 there, because next is the decrease, so it has to go down. And it has to cut through 0, because that's where the maximum value was. And now we have another decreasing part on the other side. So that's going to be this. So I have a decrease, which means I'll have a negative derivative. Derivative has to follow the asymptote as well. I have increase, which means I will have positive. But because I have a maximum over here, I have to go through the 0 point. So I draw this way to hit that point and to follow the asymptote. The next part is decreasing, which means that from this point we'll continue into negative values for the derivative. And finally, this part of the line here is decreasing, so I need a negative value again, and I have to follow the asymptote, and I have to be in a negative, so this is the only way you can put this thing together. We don't have the function for this in terms of x squared or sine or whatever. We don't have a function, but we have enough knowledge to just say, oh, decreasing piece, derivative is below x-axis. Increasing piece, derivative is above. Min, max values, that's where the derivative would cut through x-axis. Decreasing part, so negative. Another decreasing part, negative. There's a lot of decrease here. That's decreasing, that's decreasing, that's decreasing. There are 3 decreasing parts and 1 only increasing. And that's the only one where you can find derivative above x-axis for the increasing part. All other parts are decreasing, and it's going to be negative underneath. That's it. That's the whole lecture on figuring out the derivative graphs, sketching derivative graphs, looking at the original graphs, and then you do that, use it for analysis, right? If this graph is the graph of money making, let's say, losing, gaining, losing, losing, very simple, right? Because I just need to know whether derivative is above or below x-axis. If it's above x-axis, the function is increasing, I'm making money. If it's below x-axis, function is decreasing, I'm losing money. So it's much faster to just say, oh, I know the derivative is below, derivative is above, derivative is below, derivative is below. So sell, 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 right? Walk away, spicy. That's it. Bye.